Good afternoon, everyone. My name is Paola Cavallaro. I'm from Politecnico di Torino, a PhD student from Politecnico di Torino, and you already have been introduced to the name of my research. So I just wanted to specify that the research is in collaboration with the University of Aquila and also with a third partner that I will introduce in the next slide. So the research is part of a wider framework which has the aim to support sustainable tunnel maintenance through data-driven decision-making. So specifically, the paper objective was to assess and collect, so to gather environmental impact data of tunnel maintenance intervention to be then used during the decision-making phase. This paper was possible thanks to the data provided by Tecne, which is an engineering company in Italy, managing the maintenance, the design and also the maintenance of the highway infrastructure and therefore also tunnels. Just a bit of context, so some motivation that brought our attention to this type of topic. First of all, most of the Italian infrastructure were built over 50 years ago, so they are entering a sort of a critical phase of deterioration. And for this reason, also the Italian minister just in 2022 released a set of new guidelines specifically related to tunnel maintenance, tunnel management, in which they encourage the use of preventive maintenance. So the focus is on the decision-making phase. So it's important to understand when, where, and how to intervene. And also, of course, we have to also say that the construction sector is one of the biggest contributors to the greenhouse gas emission. So our case study are 3 small-scale maintenance intervention, all targeting the same type of defect, which are cracks in concrete tunnel. And here you can see the specifically the 5 defects provided by the guidelines on which the intervention can be applied. The maintenance intervention, as I said before, were supplied by the Tecne engineering company, and they, the company used to call them with the acronym IMS, that translated from Italian means Extraordinary Maintenance Intervention. Specifically, we selected 4 of them, 4B, 4C, and 5A. The 4B and 4C are really similar. They both involves the micro drillings and also epoxy injection and then sealing the crack. But the 4C also adds some steel bar, while the 5A is a completely different approach in which we have some cement matrix and also PBO mesh reinforcement, but we will see them in detail later. So in order to gather this environmental data, we use the life cycle assessment methodology. According to the ISO 14040 and 40044, we use CIMAPRO as a software and therefore the EcoInvent database. In accordance with the standards, we followed the 4 main steps, so goal and scope definition, inventory analysis, impact assessment, and interpretation. At this point, the goal is quite clear. It was to be able to compare the 3 interventions also on an environmental perspective. We assessed in this phase the functional unit at 1 meter of crack. We defined the system boundaries that include the product stage, A1 and A3, and also the construction process stage, A4 and A5, so transport and construction site. And we also made some assumption, since we didn't know a specific construction site. We just set an average distance for the transportation set at 250 kilometers. And also we used some average value for the construction equipment took by the literature. So then we move to the inventory analysis, in which it's necessary to understand all the output and the inputs of the system. So the first step was to understand all the single stage of each intervention. So for B, for C, again, surface preparation, execution of micro drillings, followed by injection of epoxy, and then sealing and closing of holes. But in the 4C, we also add in the drilling some steel bars. While the 5A, we have different layers of cement matrix and PBO mesh reinforcement. Once all the stages were clear, we then defined all the materials and process necessary for the intervention. And we linked all the material in process to an entry of the eco-invent database. So this was the base of our calculation. The first of the life cycle assessment are the definition of the impact categories, and these are the one we used. And finally, the interpretation, so basically the results of our study. In the slide, you can see a chart where it's possible to understand the contribution of each intervention to all the impact categories. Regarding 4B and 4C, as we could expect from the beginning, 4C has a slightly worse performance than 4B due to the fact that it uses steel bar, while 5A generally performs better across most of the impact categories, for example, global warming potential and also water use. Another type of input can be this one, so where we can break down all the different contributions in each intervention. So for each intervention, it's possible to understand the single contribution coming from the materials, from the construction machinery, and also from the transport. And from this type of, from these charts, it's possible to understand, it's clear that 4B and 4C are mainly related to the high impact material they used, while 5A it's really influenced by the transport and the construction machinery. So maybe it's important to know that if we change the assumption, the results may change. And then finally, I think one of the most important limitations to underline is related to the functional unit we used. Since we decided to use 1 meter of crack, it's fine for the paper, for this paper, so for the comparison of the free intervention. But in the real world, the maintenance intervention are planning based on not on a single defect, but neither on a whole tunnel, but they basically take the tunnel and they subdivide the tunnel in segments of 20 meters. So the idea is to try to align the research with this type of approach in order to be used in the real world. And this brings to a sort of a new, a new outlook, because once you consider an entire segment of 20 meters, of course, you have to take into account different type of defects, so maybe infiltration, spalling, and other stuff. So we were planning on integrating this data, environmental data, to an instant segmentation by neural network that we already presented yesterday in another session. So we are able to understand in each segment which type of defect, where they are, and once we have also the size of them, we can relate them to the impact data and find the environmental impact of the entire maintenance of the segment. And that's it for me. Thanks for the attention.